In this last video, we're going to talk about binary liquid mixtures, and this is where we really start to blur that line between solvent and solute, and where we end up in a situation where the vapor pressure of both components matters. So, we are still talking about solutions. However, that solution is made from mixing two liquids together in usually large amounts, enough of both that we we end up just categorizing it as a binary liquid mixture in order to do calculations for things like vapor pressure over the solution, because the vapor pressure of both components matters. However, you technically already know how to deal with these, with the way that we've set up our vapor pressure calculations. So it's just that we're going to bring it all into one piece together and apply some equations that you do already know. So I've got my picture of my binary liquid mixture. I've got, X's and O's in solution, and I've got a closed system. Right, we're going to actually make this a closed system so that when we get an equilibrium with the vapor phase, we're very strictly specifically talking about vapor pressure over a solution as it was defined a lot earlier. So for Raoult's law, this applies individually to the components of the mixture. So the vapor pressure due to component X is the mole fraction of X in the liquid times the pure vapor pressure of component X. Exactly like we did before. It's just that component O also has a vapor pressure because it is some sort of semi-volatile liquid. So the vapor pressure over the solution due to component O is the mole fraction in the liquid of component O times the pure vapor pressure of component O. So that is how you find the vapor pressure for each component. Now, we'll usually end up asking for the total vapor pressure over the solution, but this you already know how to do. If I want the total pressure in a container, which in this case the container happens to be the space between the lid and the liquid, I just need to add up the partial pressures of the things that are there. So we can combine Raoult's law with Dalton's law of partial pressures to have, right, the total pressure is the pressure due to X plus the pressure due to O. I could then do a substitution into this equation. For pressure of X, I could substitute with mole fraction in the liquid of X, right? So these are all going to be combined for our binary liquid mixtures. So I guess in words, what has already kind of been explained, each liquid has its own vapor pressure. The pure vapor pressure that then you use the mole fraction to figure out how much it contributes to the total vapor pressure. If you have a more volatile liquid, it will contribute more to the vapor pressure over the solution because the pure vapor pressure is higher. So, right, if you have two different liquids that have two different volatilities, this, if we were talking about separate samples, you would completely expect this, right? More volatile, we're using that to describe things that usually have weaker intermolecular forces. More is able to go into the vapor phase at a given temperature. What this means for a binary liquid mixture is that the mole fraction in the vapor and the mole fraction in the liquid are not equal to each other. There may be a case, I guess, if you had things of equal volatility, it could be possible, but in every case that we are going to encounter, that will not be possible. So the mole fraction in the liquid, that just depends on how we made the liquid to start with. The mole fraction in the vapor depends on the volatility of the liquid. Okay, we're going to do an example. I have, for this section, what it seems like is we have a couple of separate equations. Some other partial pressure equations kind of come back to haunt you, and everything ends up being start with the basics of what you know, substitute in what you can, see what you get out of it, and then figure out what you have left to do. So let's go through an example and calculate the different types of things that you would need to calculate for a binary liquid mixture. We have a mixture that contains 50 grams of ethanol and 50 grams of water, and I give you their molar masses. Find the vapor pressure over the solution. So this means find the total vapor pressure over the solution, and we have the pure vapor pressures of each of these components. So the vapor pressure of the water will be the mole fraction in the liquid of the water times the pure vapor pressure of water. The vapor pressure of the ethanol will be the mole fraction in the liquid of ethanol times the pure vapor pressure of ethanol, and then the total is those two added together. So the mole fraction, we should find first because we already have the pure vapor pressures. 50 grams of water converted to moles is 2.775 moles, and 50 grams of ethanol converted to moles is 1.085 moles. So the mole fraction of water in the liquid is 2.775 divided by those values added together, which is 0.719. And the mole fraction in the liquid of the ethanol is 1.085 divided by those two numbers added together. So we get 0.281. Or the thing about mole fractions, right, this is just the decimal version of the percentage. So the mole fractions have to all add up to 1 or add up to 100%. So once I calculate the mole fraction in the liquid of water, I can find the mole fraction in the liquid of ethanol by doing 1 minus the mole fraction of water. So this is similar to what we did with weighted averages with isotopes, where the percent abundance of the isotopes had to add up to 1 or add up to 100%. You can and will need to use that same principle here with the mole fractions of the components of the binary liquid mixture. So my pressure of water is the mole fraction times the pure vapor pressure. So I get 17.05 torr. For ethanol, mole fraction times the vapor pressure, I get 16.66 torr. And I have this highlighted here, right? In terms of mole fraction, 0.719 for water, 0.281 for ethanol. There's a lot more water in mole terms in this solution, but the vapor pressure of ethanol is so much higher than the vapor pressure of water that we get pretty near equal contributions to the vapor phase from the components in the liquid. All right, so add those two together to get the total pressure. The total pressure is 33.71 torr. 17.05 of it coming from water, 16.66 of it coming from ethanol. So the next question says, what is the mole fraction in the vapor for each component? So the equations that will help with this, the pressure, so in my total system, and this is something that we've used, now I'm dealing with just gases. I want to know the mole fraction in this gas sample. We have had this equation before. We may not have really needed to use it, but the total pressure, the mole fraction will tell you kind of like the percentage of the total pressure, right? Those two things are related. So the pressure due to water is going to be the mole fraction of water in the vapor times the total pressure. And the pressure due to ethanol will be the mole fraction in the vapor of ethanol times the total pressure, right? So higher pressure, higher moles. We have, right, I kind of pointed out they're near equal. We're going to end up with near equal mole fractions in this case. So, and I don't have numbers fully plugged in yet. I did a little rearranging to also kind of show you, and since this is what we're going to solve for, this mole fraction in the vapor of one of the components, it's the partial pressure divided by the total pressure. That's all related to Dalton's law of partial pressures. So this did come up when we did gas laws in the previous semester. But right, this is another relationship between the partial pressure and the total pressure that tells you about the number of moles related to the moles of the whole sample. So for water, that means 17.05, which was the partial pressure, divided by the total pressure, which is 33.71. I get a mole fraction of 0.506, and then I could do the division or I could do 1 minus. The mole fraction of the ethanol in the vapor is 0.494. So more volatile component, it was only less than 30% of my liquid mixture, but it's nearly 50% of my gas mixture because of that volatility.